Hello and welcome back to the course on machine learning. In the previous tutorial, we talked about the hierarchical clustering, the intuition behind it, and how it works. But at the same time, we didn't quite understand what the whole purpose of HC was and what the benefit of it was. Yes, we went from a huge amount of clusters where every single point or data element was considered a cluster, and then to one big cluster. But as a result, now we have one huge cluster. What's the point of all of it? How do we get to the result we want, the actual clustering? So like in k-means, for instance, we would have 2 or 3 clusters. How do we get to that right number of clusters? So this is where the dendograms come in, and they'll help us understand everything. Let's get started. So here I've got a chart on the left, which contains 6 points. And on the right, I've got another chart. We're going to use this chart to create a dendrogram. Now, I know it might sound a bit confusing at first, especially because we haven't talked about dendrograms, but through creating one, we will learn what they are. So first off, just to make things a bit more legible, I'm going to add the points at the bottom so that they're a bit bigger so we can see them there. And so there they are.
Can you guys please keep your microphones in mute mode?
There they are, the points just listed on the bottom. On the vertical axis, we've got Euclidean distances, and it'll all make sense just now. So we're going to now go through the HC algorithm and slowly create those clusters. So to start off with, every single point is an individual cluster, right? So every single one of these points is an individual cluster. Next, what we're going to do is we're going to find the 2 closest points, which are these 2, and put them into one cluster. So that's our step 2 in our algorithm. So there we go, that's the 2 closest points. And now we're putting them into one cluster. Now, what we want to do on this diagram here, on the dendrogram, is we want to somehow signify that these were indeed the 2 closest points, because the dendrogram is kind of like the memory of the HC algorithm. It's going to remember every single step that we're performing. So there they are, those 2 points, P2 and P3. How do we signify that we've just connected them and that they were the closest? Well, to connect them, we would use like a horizontal line, but then where would we put it? Would we put it at the very bottom? Would we put it a bit higher? What's going to determine the distance, how high we're going to place this line? So this line is actually placed this height actually has a meaning. This height is the Euclidean distance between them, and it also represents the computed dissimilarity between the 2 points or the 2 clusters. And what that means is the further away 2 points are, so for instance, P2 is that far away from P3. And this could be a variable, for instance, could be the age of a person. Right, and this variable could be, for instance, the salary of a person, right? Or this variable could be how long a person has been with the company, and this variable could be the salary of the same person, so something like that. So basically, we can see that P2 and P3 they have that distance between them, well, whereas P2 and P4 have a greater distance between them, and that means that these 2 points, P2 and P3, they have a certain dissimilarity, which is measured by the distance between them. So the distance represents the dissimilarity between the 2 points. And P2 and P4 also have a dissimilarity, and it's greater because you can see that the distance is greater. So let's say if this was age and this was salary, these 2 points, even though they're not identical, they are less dissimilar in terms of age and salary than P2 and P4. And again, these variables are just arbitrary. I'm just calling out arbitrary variables. They could be anything else, and this data set could not be employees, it could be machines, it could be certain observations from nature, and pretty much anything. The point here is that the further away 2 points are, the more dissimilar they are, and that is being measured or captured in our dendrogram by the height of this bar, how high we're setting it. And then the bar itself just shows us that we connected P2 and P3. All right, so that's our first step in the dendrogram. Next, we're going to move on, and we're going to proceed to the next step in our HC algorithm. We're going to perform step 3. So we're going to find the next 2 closest clusters and connect them. So here we've got each point out of these 4 is a cluster, and then we've got this cluster. Now we need to find the 2 closest out of all of them. And let's say, or from what we see, these 2 are the closest. So let's outline them. There we are. And so now they form their own cluster. Now we want to point that out in the dendrogram as well. So again, we're going to place this horizontal line. Again, how high do we place it? Do we place it higher or lower than this line? Well, we agreed that this vertical axis represents the Euclidean distance, and Euclidean distance represents the dissimilarity between two of our observations. So here we can see that P5 and P6 are actually further apart than P2 and P3, and that is of course natural, because if P5 and P6 were closer, then in the previous step we wouldn't have put P2 and P3 in one cluster. We would have put P5 and P6 in one cluster. Remember, we're always looking for the closest, and then we're moving on to the next step. So P2 and P3 were the closest, and that's why this distance is such. P5 and P6 are further apart from each other than P2 and P3, so the distance has to be greater. And that's why we're going to show that on the dendrogram, this cluster than to any other cluster. And pretty much out of all the distances between the clusters, this is the lowest. Again, a lot here is determined by how you measure distances. You can see that the distance between P4 and this cluster is quite close to this distance, but we're going to say that this distance is the lowest. All right, so what we do next is we combine these clusters into one cluster. Let's do that. There it is. So now we have one cluster. Now we need to represent that somehow here. So what we just did is we took this cluster that we have, P2 and P3, connected it with P1. So again, we're going to draw a line, and we're going to draw our vertical lines here again. And once again, the distance here from P1 to the top over here represents the dissimilarity between that cluster that we had and what's the point that we connected it to. All right, so now let's connect, let's find what's the next step. Next step, again, is step 3, and we're going to look out of 1, 2, 3 clusters that we have, which are the closest? Well, obviously it's P4, and it's the closest to these. Again, there it is. We're expanding that cluster. And now we're going to represent on the dendrogram. As you can see, the line is about the same height as this previous line, because the distance between P1 and this cluster was about the same as the distance between P4 and P5 and P6. Maybe this one was a bit greater. Sometimes it's hard to tell, and that's why we have algorithms. That's why machines do it for us. One of the reasons. That's what our dendrogram looks so far. And our final step is to combine these two remaining clusters, because by default they are going to be the closest since there are no other clusters. So we're going to combine them and represent that on our dendrogram. So here the line is very high because the distance or the dissimilarity was very high between these two clusters. And there we go. So that is how we construct our dendrogram. Slowly from the bottom up it's being constructed, and at the end we've got that one cluster. So all of this is one cluster. And that is what I mean when I say that the dendrogram contains the memory of the hierarchical clustering algorithm. So you can, just by looking at the dendrogram, understand in which order these clusters were formed. And here I've got an example. So this is the actual example generated by computer, generated by an algorithm, showing us the hierarchical clustering. So we've got the points here, and we've got the dendrogram over here. So this is what it actually looks like. All right, so now we know how dendrograms are constructed. In the next tutorial, we will learn how to use them to enhance or actually execute.
So here it is about agglomerative clustering. Coming to the another divisive clustering, if you start with entire cluster, so let us assume your install step is the last step of this thing. So here finally we have this entire cluster, right? From this entire cluster, if you proceed from starting onwards, that is nothing but if you start from top, if you move to the bottom, that is called as divisive clustering. So here it is an example for agglomerative clustering.
Our hierarchical clustering algorithm. An example, the example that we looked at previously, so these bars, we all of this thresholds. We don't, which also represents the dissimilarity between them, or points or clusters. So what we can do is set a threshold for our dissimilarity, and we can say that we don't want dissimilarity to be greater than this level. So again, it doesn't matter what the absolute value is; it matters what the relative value is and how it looks on this image. So we're setting the dissimilarity threshold. We're saying that anything, if we come across clusters that are above this threshold. So we don't want within a cluster to have dissimilarity above this threshold. So what that'll do is it'll give us two clusters. Let's have a look at them. There's our first cluster and there's our second cluster. And that makes sense. So what that is telling us is that within each one of these clusters, the dissimilarity is always less than our threshold. So let's say we've got some values here. Let's say this is 1.5, this is 2.0. So let's say we want to set the threshold at 1.7, and what this is doing is it is not allowing any clusters that would have dissimilarity of greater than 1.7 within them. And as you can see from the dendrogram, we can tell that everything below.
So remember one thing. So here, based on the maximum dissimilarity line. So if you observe all these lines, here we have maximum distance. For this line, here we have maximum distance. So for this maximum distance, we are drawing one line. So this line is called as threshold line. So here, whenever this line meets to this vertical line, whenever this horizontal line meets to this horizontal line, that point is called as, here this point is called as threshold point. That is nothing but it is one cluster. After this, we have one more cluster. So here it is meeting one more time here. So here it is one more cluster. So here it is moving first time here and it is moving second time here. So these two are the different clusters. That is nothing but this category. So after that, if you draw one more cluster here, if you draw one more line from here, it will become one more cluster. Like that, if you draw one more line here, if you draw a line from here, well, how many clusters will be there? Here it is one cluster. Here it is one more cluster. 2, 3. Sorry. Yeah, we will see that thing.
That level, this cluster and this cluster, they don't have dissimilarity of 1.7 because dissimilarity is represented by these vertical lines. And that's how the concept of thresholding works. And the interesting part about dendograms is you can quickly tell how many clusters you will have at a certain threshold by just looking at how many vertical lines this horizontal threshold actually crosses. So here you can see it crosses 1, 2 vertical lines. That means we will have 2 clusters. It will be this cluster with all these points, P1, P2, P3, and this cluster P4, P5, P6. All right, so let's have a look at another example. Let's have a look at an example where we put the threshold at this level. So somewhere just below where we combined, as you remember, we had P5, P6 in one cluster, P2, P3 in one cluster, P4 by itself, P1 by itself, and then we combine P1 with this cluster, P4 with this cluster. So let's say we're setting the threshold at just before that level of dissimilarity, which allowed us to combine P1 with this cluster and P4 with this cluster. So what that will do is it will give us a certain number of clusters. So can you tell just by looking at the dendrogram how many clusters we'll have? Exactly correct. We're going to have 4 clusters because it crosses 4 vertical lines. 1, 2, 3, 4, right? So we're going to have a cluster P1, cluster with P2 and P3, cluster with P4, cluster with P5 and P6. Let's have a look. 4 clusters, and there they are. So that is what we're going to get if we set the dissimilarity or distance threshold at that level. Let's try another one. Let's say we want to set our dissimilarity threshold very low, at 0.3, meaning that we don't want clusters that have any points within them that have dissimilarity greater than this threshold. So we're not going to allow any clusters like that. And the interesting part here is that we're actually setting the threshold below our very first cluster that we created over here, P2 and P3. So we're not even going to allow P2 and P3 to be combined in one cluster. We're going to say that dissimilarity level, that distance between them is too great, too high. We don't think.
So remember this thing. So here important thing is fix this dissimilarity threshold. Where to fix similarity threshold? So that is based on the Euclidean distance, maximum Euclidean distance having line. So if you observe this example here, it is a similarity having line or maximum Euclidean having line. So we need to draw threshold. We have, so here it will be an optimum line. So here if you draw threshold like this, so here it is an optimum line. So if you draw threshold like this, so then this will become one cluster and this will become one more cluster. So first one become one cluster and the second one become one more cluster. So here these are the clusters. So we will discuss these things, how to draw this optimum clusters. So I will explain you this thing. Yeah, we will see same thing in the program. So here how I am taking the optimum number of clusters. So based on maximum Euclidean distance having line, I am drawing one horizontal line. I am keeping this one as a threshold line. So whenever this to the vertical line, that will be considered as one cluster. But this will be considered as one cluster. And here again it is meeting at this location. And this will be considered as one more cluster. So here we have cluster with P1, P2, P3 points, and we have one more cluster with P4, P5, P6 points. So in this example, it is a thing.
That based on level optimal, this explains that you can this total matter where you said you can one of the scatter plots. So for instance, we'd like to know, even without seeing the scatter plot or the data set at the moment, we'd like to know what is the optimal number of clusters in this data set just by looking at Dendogram. Can you identify that? So if you like, you can pause the video and just look at these vertical and horizontal lines and try to find out, based on the method that we discussed, what would be the optimal number of clusters. So in 3, 2, 1, I'm going to now reveal.
If you draw an optimal line, if you consider what are the maximum Euclidean distance having clusters. So here if you observe this thing, you might think it is an optimum distance or maximum distance having line. No, you need not to consider that thing. You need to consider minimum length having line. So if we consider this line, it is having, okay, it is having good dissimilarity only. Whereas coming to this thing, it is a smaller line only. That's why here we have maximum distance. That's why I am considering this one as in my threshold line. So here in this example, I am keeping this one as in my threshold line. Now I will draw my threshold line from this thing. So here I am drawing threshold line from here. So here it is meeting first time here. That is nothing but here we have cluster 1 with the points P1, P2, P3. And here it is meeting at this location. That means with the P4, P5, P6, we have one more cluster. So again, if you observe this thing here, we have P7, P8, P9 points. So with this, we can create one cluster. That means here it is this line meeting vertical lines 3 times. That means here we are having 3 optimum clusters.
How I would solve this challenge? Well, what I would do is I'd look for the longest vertical line that doesn't cross any extended horizontal lines. So if you extend that, extend that, extend that, you can see that it's probably this line over here. And so that's the largest distance. That means we need to cross it with a horizontal line with our threshold, and that will give us the number of clusters, which is 3 clusters because it crosses 3 lines here. 1, 2, 3. And if we look at the chart, as you can see, indeed, we do have 3 clusters. And it does look like that is the optimal number of clusters for this problem. So hopefully you enjoyed this tutorial. We walked through all of this manually so that
we will discuss the project with the same data set. So we will perform same clustering by using hierarchical clustering. So how to do that thing, we will discuss now. So here previously we discussed k-means clustering, right? So like that we will discuss hierarchical clustering itself. So here I did project already for this hierarchical clustering. So here what we need to do, initially we need to input essential libraries. After importing essential libraries, we need to read our data set and we need to take our features. That is nothing but our inputs. So after that, we need to plot our dendogram. So here we need to plot our dendogram. So to plotting this dendogram, here I'm taking one more module head, that is scientific Python module. So here from the scientific Python module, here I am taking help of clusters. So here scientific Python is a module which is used to perform mathematical computations. Those who are very poor at mathematics, they can go with the scientific Python module. There you can design any machine learning algorithm also. So here by using SciPy module, in this we have cluster. In this cluster, we are importing hierarchical clustering. So from this cluster, we are using hierarchical clustering and we are importing this hierarchical clustering as SCH. We are importing this hierarchical clustering as SCH. So here it is about importing hierarchical clustering dendogram. After that, we are creating the dendogram. So by using this hierarchical clustering, here we are creating dendogram. So here for that purpose, here I'm saying sch dot dendogram method. In this we have dendogram method. We are calling that dendogram method. So in this we have linkage algorithm. So here we have linkage algorithm, which is used to take a so here which is used to classify the cluster, which is used to cut the cluster. Previously we took we divided the clusters by drawing the line, right? So to draw that thing, here we are taking help of linkage algorithm. To draw that line in the program, we are taking help of linkage algorithm. In this linkage algorithm, here we are taking x is nothing but our inputs, that is nothing but our features, and here we are specifying the method. So to calculate this distance, which method we need to consider. So previously for the k-means, for the elbow method we consider WCSS, right, within the cluster sum square. Like that, it is also one method, WAD. To reduce the variance, we need to consider WAD method. So here, in place of WCSS, we can use this WAD method also. Whereas here, in place of method, here we are trying to focusing on the reducing the variance between the different data points. So for that purpose, here we are considering the WAD method. So after considering this WAD method, after using this linkage algorithm, here we need to keep title for this dendogram. After keeping title for this dendogram, here I am keeping X label name as well as Y label name, and finally I want to show the output. So here it is the dendogram. So based on our data set points, so here it is the created dendogram. So here it is the created dendogram. So if you observe this thing, here it is a maximum threshold having line. So from this here onwards, I am cutting this line. So here I am drawing horizontal line from this here. From here onwards, I want to draw an horizontal line. How many clusters will be there? This is one cluster, and this one will be one more cluster, and this one will be third cluster, and it is fourth cluster, and it is fifth cluster. So I will draw you that thing here. So here, if you observe this thing, so this one will be one cluster, and this one is one more cluster, and this one will be one more cluster, and this entire portion will be one more cluster, and this one will be one more cluster, and this is one more cluster. So if you observe here, how many clusters we have? One cluster, two clusters, three clusters. Sorry, this entire thing will be one cluster only. So here, this entire thing will be one cluster only. So here we have one cluster, second cluster, third cluster, and it is fourth cluster, and it is fifth cluster. So here we have 5 clusters from this thing. So if you observe manually, we can observe this thing as a 5 clusters. Here I am keeping same 5. After observing that thing manually, so here I need to input agglomerative clustering algorithm. So here from the sklearn, here from the clustering family, I want to import agglomerative clustering algorithm. So here I am importing this class. After importing this class, here I am creating object with this specific class name. Here also I am specifying number of clusters as 5 and affinity to calculate this thing. To calculate the 5 points, so 5 optimal number of clusters, we are taking a method of Euclidean distance measure. So here, based on the Euclidean distance measure, whatever the things having the maximum Euclidean distance, maximum dissimilarity of 5, we are taking that thing. After that, linkage. So here, which method we are considering? You can specify WCSS also here. If you are interested to take, if you are interested to observe with the WCSS, you can observe the output with WCSS also. Whereas you can apply same WAD method in the k-means algorithm also. So with this, so here in the object, here I am specifying number of clusters and metrics which we are using, and the algorithm which constraint you are using. So here I am using WAD constraint. That's why here I am specifying WAD. After that, we need to predict the cluster from our training data. So here I am specifying the data inside this fit predict method. After that, I want to observe the output. So if you observe the output, so here again these are the different categorical points. These are the different categorical point. Again, visualization is same. So there how we did the visualization, here also in the same way we need to visualize the data. So if you visualize the data, here it is the clusters. For these different clusters, we need to keep different names. So here I'm keeping different names for these different clusters. So here these are the different names which I kept for the different clusters. So whatever the thing we did previously, same thing we need to follow here also. So here it is about hierarchical clustering. So in the next section, that is nothing but tomorrow's session, we will discuss one more concept that is called as sentimental analysis. So how to do natural language processing, how to analyze the text information. Based on the text information, how to say whether that is a positive statement or negative statement. We will discuss that thing tomorrow. With this, I am concluding. So here, those who are interested to do the project with the machine learning, so try to download some research papers. So if you have any ideas, download some research papers. After downloading that research papers, if you are comfortable to do the project, proceed with the project. If you are unable to do the project by downloading that paper, forward me that paper. So I will tell you how to proceed further and how to finish that project. So if you do your project on your own, you can get good knowledge. Thank you. With this, I am concluding for today. So someone text some message in the group. So yeah, good question. What is the difference between previous one and this one? So both are same only. Both are used for clustering problem only. So whereas if you are having huge amount of data, better to go with the k-means algorithm. Whereas if you want to work on clustering problem, if you have very small amount of data, then better to go with this hierarchical clustering model. So based on your requirement, you can proceed with the any model. Both the algorithms used for clustering problem only. So whatever the algorithm comfortable to you, you can use that algorithm. So if you want to know the advantages and disadvantages of both the algorithms, you can search in Google. You will get to know everything regarding these two algorithms. Thank you. With this, I am concluding for today.